Today we're going to review Chapter 9, Sequences and Series. Remember, sequence is a function whose domain contains consecutive integers, 1, 2, 3, 4, 5. It does not tell you what the number it starts with, but then we can assume it starts with 1. A series, we add up all the terms together of a sequence. This is also often called finding the sum of a series, or a summation function. So use summation notation to write this sum, negative 2 plus 6 minus 18 plus ... all the way up to negative 1458. Well, it looks like our initial term is negative 2, and it looks like we have a ratio of negative 3 between terms. We could figure out that this would be the 7th term. Now, I'm not going to go into that right now, but you could figure that out. So I'm going to go from n equals 1 to 7 of my first term, which is negative 2, times my ratio times n minus 1. So this is how we could use summation notation to write this sum. Okay. Arithmetic sequence. Remember that it has a common difference between each consecutive term. And we could write the nth term as a sub n is equal to a sub 1 plus n minus 1 times d. And we could write, for an arithmetic series, we could write the sum as n times a sub 1 plus a sub n divided by 2. So let's look at this. How can we write a rule for the nth term of the arithmetic sequence? Well, remember that a sub n, I'm going to use this formula here, okay, is going to be equal, a sub 1 is negative 7 plus n minus 1. My difference is 5. So a sub n is equal to 5n minus 12. How about this one? Evaluating the sum. I equals 1 to 30 of 2/3 I plus 4. I'm going to use this notation here. And what is my n? My n is 30. What is my a sub 1? Well, it's going to be 1, which is 2/3, plus 4, which would be equal to 12/3. So 2/3 plus 12/3 would be 14/3. My a sub n would be 30. So 30 times 2/3, okay, would be 60/3 plus 12/3 would be 72/3. All divided by 2. Do a little bit of math. I've got 30 times 86 sixths, and that would equal 430. Now, if you really wanted to, you could try this on your calculator to check it, but you should be able to do it without a calculator as well. Give you a second to jot that down. Okay. Now remember, a geometric sequence has a common ratio when you divide each consecutive term. Okay? So my formula for the nth term, a sub n is equal to a sub 1 r to the n minus 1 power, and my summation is equal to a sub 1 times 1 minus r to the n divided by 1 minus r. So let's take a look at some examples. Let's evaluate this sum here. I'm going to use this formula. And what do I have? My a sub 1 is 1/2. My ratio is also 1/2. So I'm going to have 1/2 times 1 minus 1/2 to the 5th power, because that's my n, divided by 1 minus 1/2. I've got 1/2. 1/2 to the 5th is 1/32. So 32 over 32 minus 1 over 32 is equal to 31 over 32. 1 minus 1/2 is 1/2. The 1/2s cancel out, and I'm left with 31 over 32. And again, you could check that on your calculator if you wanted to. All right, so let's write the rule for the nth term. We're just going to use this formula here. And my a sub 1 is 3. My ratio is negative 2/3 to the n minus 1 power. Okay. Now, we also talked about the sum of an infinite geometric series. Remember my ratio, my absolute value of my ratio has to be less than 1 in order for this to converge. Okay? If it's greater than or equal to 1, it will never converge. Your answer will be infinite, but we will have a finite sum of an infinite series if the ratio is less than 1. So here I have S is equal to A sub 1 divided by 1 minus R. So let's take a look at this one here. K equals 0 to infinity of 6 times 1/3 to the K power. Well, my A sub 1 is 6. My ratio is negative 1/3, which is definitely less than 1, the absolute value. So I can evaluate this. And 6 divided by 4/3 is equal to 9/2. And if you wanted to check this on your calculator, remember there is no infinity button on your calculator, so you would have to use a large number like 100 or something like that. And you could plug that in and you should get a number that's very, very close to that, if not equal. All right, let's take a look at this example. I've got a repeating decimal here, 0.123, so on. Write this as a fraction in simplest form. Well, we can break this into threes here. And what's it going to look like? It's going to look like 123 over 1,000 plus 123 over a million plus 123 over a billion, and so on. Okay? So what is my a sub 1 in this case? My a sub 1 is 1, that should be a 1 there. 123 over 1,000. My ratio, if I look, I'm multiplying by 1/1000th every time. So I could write it this way. 123 over 1,000 divided by 1 minus 1 over 1,000 is equal to 123 over 999, which reduces to 41/33. We'll do a second jot that down. And again, you can come back and revisit this if you need to. All right. Mathematical induction and counterexamples. Remember, for mathematical induction, you might have to go back and revisit your notes on these. But to prove that a statement is true for all natural numbers n, we first have to prove that it's true for n equals 1. That's the base case. Then we take some number in the statement k, prove that it's true for that, and then prove that it's true for k plus 1. So now we often use counterexamples to disprove a statement. Okay? There cannot be more than one possible answer for a counterexample, but all we need to do is find one example where the statement is not true to disprove the entire statement. Okay, I'm not going to go into any examples right now. You can go back and check your notes on those if you need that to fill out the study guide. But counterexamples, helpful hint, can often be found using special numbers like 1, 0, negative numbers, fractions, and the like. So we're going to stop here for today and let's work on the next section in this study guide.